Hello! Welcome to West Virginia! Maybe not. No. Anyways, joke of the day, because it's the best part of the day. So what did the hat say to the tie? Well, he said, you hang around, I'll go on ahead. Alright, so let's go on ahead to quadratic functions. So a quadratic function is a situation represented by a curve, and oftentimes when you talk about projectiles, the path of the projectile would be a curve. So for instance, if you're talking about like an arrow, even though it seems like the arrow goes straight, the arrow actually is going to kind of curve down as it goes. Shooting a basketball takes the path of a curve. Even a missile will take the path of a curve. So anytime you're talking about a projectile, that projectile takes that path of a curve. It is represented by a quadratic function. This is what a quadratic function looks like. Now, what we're used to seeing, what we talked about before when we talked about solving quadratics, this was a y. But you know that whenever you have a function, that means that it meets the vertical line test. Vertical line test says that graph, whenever you drop that vertical line through it, then that indicates that it's only going to pass through the graph one time. If it passes two or more times, then it's not a function. So when you know that the graph passes this vertical line test and you know that you have a function, then what you do is you say, I'm going to replace that y with an f of x. But the f of x is acting like a y, so it has the same feeling as a y, but when you see that notation, you go, okay, this one's special. This one is a function that's going to match that vertical line test. Anyways, so here is my function. Notice that I have a squared term right here with my x squared, first power term right here. The other definition of your quadratic is that your a, your b, and your c are all actually going to be numbers. The only thing in here that's a variable is the x. And your a and b and c are all going to be real numbers. Now that we understand what complex numbers are, we understand the importance of knowing that there are not going to be any imaginary numbers in these coefficients nor in this constant back here. In addition, the a, the coefficient of your x squared term, is not going to be 0. Because think about it, if that a was a 0, what would happen to this term right here? Oh, absolutely, the term would be gone. You would no longer have a quadratic, you would have a linear function. So it's very important that that a is in there. You have that squared term to make it a quadratic. Now, like I said, once we know that we have a quadratic and we know that we have a curve that we're dealing with, we can call that curve, we do call it a parabola. Not that we can, but it is called a parabola, or as I like to call it, parabolas. Anyways, in this situation, because our squared term is on an x, then that means our parabola is either going to curve up or curve down, plus the fact that we have a function. Because if it curved to the left or curved to the right, it would no longer be a function. So our parabola is either going to curve up or it's going to curve down. Notice that we have a turning point right here down at the bottom, or we have a turning point up here at the peak. That turning point is what we call the vertex of the parabola. So basically what it does is it shifts the direction of the parabola. And this one, it's coming down, 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 bottoms out, and then starts curving back up. So we have that bottom out point as our vertex. In this situation, it's coming up, 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 and then it peaks, and then it starts curving back down. That peak point is what we call our vertex. Now, we have what's called the simplest form of a parabola, or simplest form of quadratic, that is. The simplest form, notice here, f of x equals ax squared, takes out your first power term, takes out your constant term. So when it is just f of x equals ax squared, there's certain properties that we can bank on with this parabola. Certain properties we know without a doubt or we are going to see. The first of those properties is we know where that turning point is going to be, and it's always going to be at the origin of the graph. So in other words, if I was to graph this parabola, I know without a doubt it's going to have that bottom out point or peak point, depending on which way it turns. It's going to be sitting right there at that origin. The other interesting property of your parabola is whenever you have the simplest case, or actually you're going to see in any case, but it's now we can figure out which way it's going to turn, whether it curves up or it curves down. The way that you figure that out is you take a look at this coefficient of your x squared term. Now, I'm stuttering on my words. But anyways, mathematicians, everybody thinks we try to make things really hard. We actually don't. We try to make things very easy, in fact. And so it's kind of commonsensical to think, okay, if that a is greater than 0, meaning it's a positive number, then it stands to reason probably which way would this thing open. Exactly right, it's going to open up. So in other words, if that A is positive, then my parabola is going to open up and it's going to look like this with a vertex at a bottom out point. So by that same token, if that A is less than 0, in other words, if it's negative, stands to reason which way is it going to open. And you're exactly right, it's going to open down. And so that means my parabola is going to look like this, so it's going to have a peak point right here. So that means if I have one in the simplest form, and I know my vertex is sitting here, it's either going to open like this, or, and that's in the case where that coefficient on the x squared term is positive, or it's going to open like this. And that's the case where the A is a negative. Notice that it is symmetric with respect to that y-axis. Now, what is symmetry? Symmetry is the idea of being able to fold on top of itself. So in other words, if this parabola has symmetry, that means this side is going to be able to fold right on top of the other side, and it's going to lie right on top of itself, or this side is going to fold right on top of this side, and it's going to lie right on top of itself. What's its folding line? Right through here, which is your y-axis. And that is your symmetry line whenever you've got a parabola in that simplest form. So let's take a look at an example of the parabola in that simplest case. And take a look at what we've got right here. And it says that I'm going to take that parabola, I'm going to graph y equals 2x squared. Well, first I need to figure out where that vertex sits, and then I need to figure out which way it opens, and then I can actually do the graph and use symmetry. I'll only need to get one half of the graph, and I'll use symmetry to get the other half of the graph. So because it's in the simplest case, and I don't have that first power term, I don't have the constant term, that guarantees without a doubt I know that vertex is sitting right here at 0, 0. So I know that my turning point is going to be right here at that origin. So I just need to figure out, is this thing going to curve up or is it going to curve down? Where do I look to figure that out? Absolutely. Look at the coefficient of my x squared term. Notice that that coefficient is a positive 2, and because it is positive, that means that it's going to open which way? Sure, mathematicians are not creative. We try to make it easy. If it's positive, it's going to open up. So I know that my parabola is going to open like this. I'm just not really sure, is it going to be skinny like this or is it going to be wide like this? The only way to figure that out is to just start putting some points in there. This is where that point plotting method is very handy. Remember, the point plotting method said, let's pick some values for x, let's put them into the equation, see what y values spit out. That creates an ordered pair. I can put the ordered pair on the graph. Now, what I always say is the best thing to do with point plotting method is to pick a couple of negative x values, a couple of positive x values, pick that 0. That way you can get a nice pretty picture as to what the graph is doing all the way through the 2D coordinate plane. However, because I know that I've got symmetry on this thing with respect to that y-axis, I only need to get one half, and then I'll fold it across that y-axis to get the other half. So in other words, I don't really have to get all these negatives and all these positives. As a matter of fact, I'm going to make my life easy. I'm going to pick positive numbers because they're easier to work with. So I'm going to pick, say, for instance, a positive 1, a positive 2, and even a positive 3. That will be enough to see what's happening over here, and I'll flip it across the y-axis to get the rest. So that means that I'm going to take my function 2x squared right here. I'm going to put a 1 everywhere I see an x. It's going to spit a y value out. And then recall that's going to give me some ordered pairs, and I can put those ordered pairs on the graph. So when I put a 1 in here, this is what I have. An order of operations says do the exponent first. 1 squared is 1, and 2 times 1 is 2. So that means in this case, when x is 1, y is a 2, and that's going to sit right here. Now I need to figure out, okay, when x is 2, where is it going to sit? So I'm going to put a 2 everywhere I see an x, and once again I'm going to follow this order of operations, which says let's do the exponents first. 2 squared is 4, 4 times 2 is 8. So when the x is 2, the y is an 8, and that's going to sit right up here. And apparently I did not do a good job of setting up my 2D coordinate plane. Let me do a better job here of getting that set up. I'm going to need a lot more space than that. So I'm starting here at 0, 0. And I've got a point at 1, 2, and 2, 4, 6, 8. 2, 8 sits here. Okay, so now let's put a 3 in there. Once again, that means take the x out, put a 3 in its place. And when I do, then I need to follow order of operations, which says do the exponents first. 3 squared is 9. 9 times 2 is 18. That gives me an ordered pair of 3, 18. So that means that my other point sits at 3 and 2, 4, 6, 8, 10, 12, 14, 16, 18 is going to sit up here. And there we go. So I know that this side of the curve looks like this if I did a decent job, and I'm not doing that great of a job. And I could pick negative values, but remember I have symmetry, so I can just take this and fold it across. And what that means is where this was a positive 1, 2, now I've got another point here at negative 1, 2. Where this was a 2, 8, now I can flip back to negative 2, positive 8. And where this was a 3, 18, I can flip it back to negative 3, 18. That creates the other side of the graph that looks like this. And I need to make sure that I understand that this is not a perfect little V point. It's actually going to be a little bit better of a curve than this. And that's what your parabola looks like. And you know that I like to put my little smiley face in there just because it makes me happy. But you don't have to do that. But this is how you graph a parabola that's in that simplest case. Your vertex is at 0, 0. Figure out which way it opens by looking at your coefficient of your x squared term. Graph a few of those points on one side and use symmetry to figure out the rest. All right, have a great day.